Well, hello everybody. Today's notes are on limits at infinity, section 11-4. These are the last notes for this chapter. So if you've understood everything so far and today's notes make sense, you are doing great. If not, let us know. We'll help you out. Okay, now limits at infinity just means take a look at this first example here. We want to find the limit as x approaches infinity of this function. Okay, this is a big idea you're going to see a lot of in calculus. We need to get this down. Now, here's the plan for the notes today. We're going to go through 3 examples. We're going to find all of these using our calculator, but then we're going to use those answers, use our insights to come up with some general rules. And with those general rules, you should be able to look at this limit immediately and tell me what the answer is. In fact, every one of you at the end of the notes should be able to come back here to example 1, glance at this, and know exactly what that answer is equal to. Okay, that's our goal. You need to know exactly what that answer is without doing any work at all. Seems hard to believe. It's true. Okay, so here's what we're going to do. We're going to graph this function. We're going to trace it. Now, as x approaches infinity, that means x is getting infinitely big. All right? And then we're going to see, what does y approach when x gets infinitely big? Okay, so over my calculator here, I'll press the y equals key. And let's type that function in. And remember, when we do that, always put parentheses around the entire top and around the entire bottom. If you don't do that, I don't know what you'll get, but it won't be what you should be getting. And if you type that in there and press graph, you may notice this looks a lot like something that we explored back in chapter 2. It's what's called a rational function. Okay, and it's called a rational function because it's a polynomial over another polynomial. Basically, it's 2 polynomials written as a fraction. Back in chapter 2, there were 3 rules for dealing with those, and we're going to see 3 rules for dealing with them now again. And guess what? Big surprise. It's the same 3 rules. So we'll see if these rules come back to you as we take a look at this. But anyways, if we graph this function, here's what we get. And I'm going to trace this. It says as x approaches infinity, meaning if I press my right arrow until x gets infinitely big, and it takes a long time, x is up to 2, 3, and you'll notice that as x gets bigger and bigger, well, you can even do this until it goes off the screen. Sometimes students just sit and do this for the entire class period. What a waste of time, people, but you could. I'm not going to stop you if you do. You'll notice why, well, it looks like it's approaching this horizontal asymptote. It's getting bigger and bigger, but where's that asymptote at? Well, let's fast forward a little bit. I'm going to set up my table. And let's start our table at 1,000. Let's just go to some really big number. And let's take a look at our table of values. Well, it looks like when x is 1,000, the value of y is 0.5986. And it looks like it's 0.5986 for quite a while. And, you know, we could go bigger and bigger and bigger. But it looks like it's getting, I don't know, close to maybe 0.6. I'm going to put a question mark next to that. We think maybe this is approaching 0.6. Okay, we'll come back to this one in just a bit. So let's leave that question mark for now, but we'll come back and get a definitive answer momentarily. I want to look at a second example. Another rational function. And in fact, when we see these limits at infinity, it's these rational functions we're dealing with. So let's graph this one. So again, in parentheses on top, I have 6x squared minus 5. Close my parentheses, divided by, in parentheses on bottom, x, I'll use my caret key to get to the 3rd power, get out of that power, plus 2x minus 1. Let's graph this one. Let's take a look at this rational function. And I could have done a zoom standard to center my axes, probably should have, but I'm just going to trace it where we're at. And you'll notice again, it looks like it's approaching an asymptote. And as x gets bigger and bigger, y is getting closer and closer. Well, it's hard to tell. I'm going to set up my table to start at 1,000 again and go to my table. And it looks like when x is 1,000, the value of y is 0.06, but really, really small. So I'm thinking, maybe this gets closer and closer to 0. Now I'm going to put a question mark there. I'm not quite sure yet. It looks like it's getting smaller and smaller and smaller. When I looked at my graph, there was an asymptote somewhere here. Maybe it's at 0. All right, let's take a look at a third example. Okay, let's find this limit as x approaches infinity of this function. Again, a rational function. I'm going to type that in and graph it. So on top in parentheses, I'm going to write 3x squared. Close my parentheses, divided by parentheses, 2x plus 9. And I'm just going to center my axes. See, standard will do that. And here we go. Okay, kind of weird if I trace this. Now, here's a difference here. If I trace this, we're not approaching any horizontal asymptote. Now, let's just think about this. We don't have to look at a table here to know that if this just keeps going upward and upward and upward, that our y value, as x gets bigger and bigger, our y value is also just going to get bigger and bigger. So it appears as if this one just gets infinitely bigger on and on forever. Okay, let's try to make sense of this. And to make sense of this, we're going to have to think back to something we did way back in Chapter 2. In Chapter 2, we found horizontal asymptotes, and there were 3 cases. One case was, if the power on top, the greatest power, the degree on top, is the same as the greatest power or the degree on bottom, this is going to approach a horizontal asymptote at y equals a over b. Now what's a and b? A and b are these numbers here. This 3, and this 5. So we're saying that since the greatest power on top and bottom are the same, it's going to approach this horizontal asymptote, in this case at y equals 3/5, which is what we expected when we said about 0.6. All right, that's kind of cool. And kind of cool, there's a connection there to first semester. Something else we learned in Chapter 2 is that if the greatest power on top is smaller than the greatest power on bottom, there will also be a horizontal asymptote. And that horizontal asymptote will be the x-axis. Well, the x-axis has the equation y equals 0. So I'm going to get rid of this question mark here, because if we see this limit at infinity, and the greatest power of the degree on top is smaller than the degree on bottom, this will always approach the x-axis, which is the line y equals 0. So remember when we traced this one, we got closer and closer to 0. Now the last one, the third case, and we got to think back to first semester, Chapter 2 again. If the greatest power on top is greater than the greatest power on bottom, there is no horizontal asymptote. This just keeps growing forever and ever. And back then we just said there was no horizontal asymptote. Here we say it's approaching, well, this infinitely big number. We already learned that we can't just say the limit approaches infinity. Instead we say, hey, the limit does not exist because it does not approach a set number. Okay, so let's summarize. Limits at infinity, here's our summary. We have 3 cases. First case, if you have a function like y equals, let's say, a x to the 5th over b x to the 5th. Notice the greatest powers, top and bottom, are the same. Okay? If that's the case, the limit as x approaches infinity is equal to a over b, those leading coefficients. Second case, if we have y equals, and let's say we have x to the 3rd on top and x to the 5th on bottom. If the greatest power on top is smaller than the greatest power on bottom, then the limit as x approaches infinity is equal to 0. This is just going to approach a horizontal asymptote at the x-axis. Third case. let's say we have y equals, and I'm going to say x to the 5th over x to the 3rd. So if your greatest power on top is greater than the greatest power on bottom. Well, this one's just going to grow infinitely big. So in this case, the limit as x approaches infinity does not exist. Okay, so if you know these three rules, you can do limits at infinity very quickly without doing any work at all. Now, I do want to point out a couple things. First of all, the other terms added or subtracted are irrelevant. It's kind of like if you had an infinitely big number, like if you had $5 billion minus 4. The minus 4 is pretty irrelevant, right? So you can just focus on the $5 billion. So any other terms added, subtracted, they really don't matter, okay? We can just look at the greatest power, the degrees, those biggest powers of x, okay? Second, and this is huge, ladies and gentlemen, these rules are only for limits at infinity, meaning if x approaches infinity, all these rules always work. The problem is people then overgeneralize and use these rules for every limit. Don't do that, okay? So these rules, they're nice, they're simple, they work every time you have a limit as x approaches infinity, and only when x approaches infinity. All right, you guys, that wraps up our learning for this chapter. So at this point, you can finish all of your homework, you can finish any review you have, and when all of that makes sense, you are ready for the Chapter 11 test. All right, take care. Any questions, please reach out, let us know, and we'll talk with you soon.